The way that I like to teach, especially math, complicated stuff, is to make it relaxed and go at the pace that you all want to set. As you put in questions to the chat, I'll try to keep an keep an eye out for them, and answer them as they come along. I'll be doing some whiteboard examples. So I think if you have a pen and paper available, it could be worth writing some stuff down. Since this is recorded, you can come back later and write stuff down. But math, I'll even say linear algebra in particular, is like the total blend between programming and writing code and mathematics. And so it's equally as important to be to understand the math side of things as it is to be able to use some Python library, Python package, Python code. And yeah, I will share my screen and get started with this notebook. Let's go to window. Okay, great. So, basics of linear algebra workshop. If you haven't used a notebook before, it's a nice way to go back and forth between writing and even using, there's a markup language called LaTeX, LaTeX, and you can use it to write math stuff like this. If I double click on this cell, there's all this, what looks like just, weird nonsense. But it gets rendered to these math equations, and you can explain things. And so it's really great for when you want to go back and forth between coded concepts. If I want to give this preface, I gave this preface last time as well. My goal for this session is to expose you to what linear algebra is in a math sense, in a programming sense. And I'm sure a lot of this will feel foreign to you in one way or another, whether it's the concepts or plenty of it can just feel uncomfortable. That's a good thing. It is good to be uncomfortable when you're trying to learn something new. It's the same deal with jiu-jitsu. It's the same deal with math, with coding. If you're uncomfortable, that's the whole, like the definition. You're seeing something you haven't seen before, and that's what makes it valuable to learn. You're expanding your horizons. So I promise this stuff isn't as complicated as it might look. You can go deeper, and that's up to you, but we're going to stick with the big concepts, what's easy to apply and to move forward with. So with that, I'm just going to get started. I know I've been talking a lot, but this first section is going to be us reviewing what a matrix is and how to do some basic operations with it. So we're going to go a little faster maybe than we did the first time, but still, if you have questions, put them in the chat. So Python, like many programming languages, has packages and libraries, and what a library is simply a toolbox for you to use. So if I want to write a program that does fancy data analysis and linear algebra stuff, I don't want to write that from scratch. I don't want to write the logic from scratch on how to do a lot of common linear algebra methods or plotting or data visualization. That would take forever. So instead, people develop libraries and develop packages, and it's your toolbox. So you can import this is called matplot library, and they abbreviate it to matplotlib. Also, let me know if this font is too small. But then we import that library .pyplot. So it's this tool that we can use for plotting later on. And then we can use as, so that when we reference this library further on in the code, we can just do plt dot and then whatever. It has functions and methods. You can get some data sets from libraries. Another one is patches you don't really have to worry about, but another one is NumPy. So it's just number Python package, very common, gives you special data types that have like many decimal places, which is common in science and math. And we import that as just NP is what a lot of people will import it as. And then SymP, which is scientific, I think, Python or something. But it's, yeah, these are just tools, is all these are. So when you run a Jupyter notebook, this notebook is shared with all of you. So feel free to keep it and use it for later. If I run Shift Enter on that cell, it's now running all these import methods, and we get that little check mark saying that it's complete. And so now for our first little taste of math is matrix addition. So everyone here, I'm sure, has seen just plain old algebra before. Linear algebra is basically taking that, like the core algebra concepts, and applying them to matrices and multiple dimensions. And by dimensions, that's like a matrix can represent multiple dimensions. I'm no longer just doing what's 2 plus 5. I'm doing what's this matrix A plus this matrix B. And so matrices are extremely useful in today's modern world because we use them to represent data. You can represent an image with a matrix. Because an image, especially just a black and white image, if you're just having, shades of white and black, that all can fit into a single matrix. And every pixel is just an entry into that matrix. So before we had computers, mathematicians came up with these matrices, and it was just a way to organize more information. But now that we do have computers, these types of matrix operations, addition, we'll get into matrix multiplication, they are performed millions upon millions of times per second on your computers. It's how, this video that you're seeing right now involves a ton of linear algebra. And at its core, that's a huge foundational piece of how computers work. There's the hardware, there's the software. This is a big part of the software, are these algorithms. And so what you're looking at here, like I said, you've got this matrix A, and it's a 2x2 matrix. Matrices have a width and a length. And if you're going to add matrices, they have to be the same dimension. And all you do to add two matrices, it's very straightforward, is I add this like top left element to the other matrix, its top left element. And 1 plus 3 is 4. So we're seeing we have this new matrix C is A plus B. And that first element is just 4. And if it seems complex, if it seems simple, bear with me. We'll get into plenty more. And that's how you do addition. It's this top right element, 6, is then added to the top right element in the second matrix, -1, and that gives us 5. So hopefully this appears straightforward to you, the A and B matrices, and then adding them together to get C. And then here's our first little taste of more precise mathematical notation. Is we can say more generally is if we have two matrices and we want to add them of the same dimensions, and matrices are usually referenced in m by n. M is how many columns, or sorry, how many rows, and then N is the number of columns. You go row by column is how you describe the shape of a matrix. And you'd say the sum of C, which is A plus B, is defined as, and then we have these little indices, I and J. And then we have this, it's the same I and J, where I is the row and J is the column. That's how we index into the matrix. That's going to be the element of C. So it's everything I just said, but now we're adding I and J as indices. So in the same way that if you're going to take like two arrays, if you've worked with arrays before in a programming language, let's say I've got an array that's just like 1, 2, 3, 4, 5. And then I have another array that I want to add. We add the first element of the array to the first element of the second array. It's just 1 by 1. So I wouldn't add 1 to 2, hopefully this is making sense. And then we say for all I, the number of rows, from the first row up to the total number of rows. And then same with J, the first column up to the total number of columns. So this element would be A sub 1, 1, first row, first column. 6 would be A sub 1, 2. It's still the first row, but it's the second column. 5 would be A sub 2, 1. And then 2 would be A sub 2, 2. So that's all that means. You have all these funky little letters on top of letters, but we're just saying add things element-wise to do matrix addition. And so if you want to see what that looks like in code, we can use NumPy, which we abbreviated as just NP. And we say A is equal to an array, and we can give, it's a 2D array because it's an array of arrays. And that creates this two-dimensional matrix. And we define it exactly as how you see it in the math notation. It's just 1, 6 as the first row, and then 5, 2 as the second row. Same thing as up here. Same thing for B. And we can print them out by running Shift-Enter. And then we can perform addition. You can see it's already been ran, but it's that easy in Python to perform the addition. If I want this new matrix, that's the sum of A and B, done. If you don't have the same dimensions, like if I take this array and now it's a 3 by 2, it's got 3 rows and 2 columns, and I try to add these, so like I've redefined A and B now, and if I try to add these, we get an error. And a huge skill in all of programming is learning how to read errors, and just do that by practice and by actually reading it. Like it's very gross to read errors. Your brain like doesn't want to do it, but it's like the push-ups of programming. It's good for you. You have to learn to read through the error, because we say we have a value error. What is it? Okay. This line, C is equal to A plus B on line 2, which we can see here. Value error. Operands cannot be broadcast together with these shapes, which is a fancy way of saying they're different shapes. You can't add them. Okay, so if we get rid of that, we run again, all is well. Any questions so far? Hopefully, matrix addition just makes sense. But if not, no problem. Go ahead and ask questions away. Okay. So now we're gonna take a step above. And the dot array call, yes, that is a function. np.array, you can see that it's like, if I get rid of these two rows, I've got my parentheses, which is, how you call a function in Python. And as arguments, I'm giving it this nested array as the argument to the function. Okay. And so back to matrix multiplication. A real world scenario of where you make a function to add matrices. There are many. Again, if you're working, like, let's say you have a video editor is a common, like, direct application of linear algebra, and you want to make a photo lighter. You just want the whole thing to be a lighter shade. Again, you can represent an image as a matrix, and it's very common to represent colors with RGB color values, where RGB is red, green, blue. You can have, like, it's just, again, it's another array. Each color is like 0 to 255. So it's just a number. It's this number of red, this percentage of red, this percentage of green, this percentage of blue. That is your 1 pixel for 1 pixel in a full image. And if I want to make the image lighter or darker or whatever, I can add another matrix that's maybe just like a lighter version. It has RGB values for all of its pixels that are lighter, and I just add it to the previous image, and that'll brighten. Once I add all of the pixel values, it brightens the image once you have your final output. Matrix addition is so core. It's like it's so fundamental that it's like the building block to, if you're building a neural network, if you're building all sorts of stuff. It's very foundational. So you use it to do things higher up the chain. And level 2 of our different matrix operations and algorithms we're learning is matrix multiplication. Addition is, as you saw, pretty straightforward. Matrix multiplication is also straightforward. It's just, if you haven't seen it, you just have to learn the steps. The way you do it is to add up the sum of multiplying the rows of the first matrix by the columns of the second matrix. So linear algebra and computer science in general has algorithms. And algorithms, to me, are fantastic, because an algorithm is it's a list of steps, and that's it. It's for given some data, given a certain situation. Here's a predefined list of steps, and just do them when the right situation occurs. The real world is extremely messy, just in every sense of that statement. Especially like when you're working at an actual software development job, it's pretty rare that you get a task and that task is like step 1 part 2, step 2 dot B. Like it's an exact list of instructions of what you're supposed to do. That doesn't exist. So algorithms, in my opinion, are really great and nice to work with, because I can define exactly what to do. Or if I'm learning an algorithm like matrix multiplication, once you learn the steps, you've learned the steps. There's it's now just a tool that you don't have to think about too much in our messy world. The algorithm stays the same. So to talk again and explain how we do matrix multiplication. I have all this math notation, but I think it helps to draw an example for this. So let's see, we've got A, that's too small. There is a great, this is webwhiteboard.com. I really like it for if you're just doing quick whiteboarding. But we've got this matrix A. And what we say, 1, 6, 5, 2. 1, 6, 5, 2. And then we have matrix B. And it's 3, negative 1, 2, 4. Okay, so I want to multiply these. I want C is equal to A multiplied by B. And just some notation that is part of linear algebra is you can also say A dot B is the same thing. A times B is equal to A dot B, which is equal to what? How do we find that? Well, like I said, we multiply the steps, the algorithm to multiply two matrices is the sum of the rows multiplied by the columns. And so to give you to walk through those steps, we will say our new matrix C is equal. Okay, so this first one, oops. I'm going to make this purple, and I'm going to make this not green, not yellow. We'll go with orange. I see why you're doing that. This is not something to put on the front page of your website. And I'm using a mouse to my credit. So anyways, we have this new matrix C we're trying to create. And yeah, of course, you have to laugh. The first element of C that we're trying to get is this top left guy, right? So we have this first row of A, and in this first column of B. Okay, so we're going to add up. It's called the dot product. But product is like the result of multiplication. We've got our dot. It's just words. We're multiplying and adding things up. So we have 1 times 3, which is going to be, I know this takes a second to draw out, but I think it helps. 1 times 3. Put it here, plus, oh, jeez. I'm losing, where am I? Sorry, 1 second. Where did my color selector go? Okay, well, that's a little annoying. I'm going to try refreshing. Technical difficulties. There we go. I don't know why that was working. So we have that first one, 1 times 3 plus 6 times 2. All right, so all of that is just our first element. Okay. So now I want the second, I want this guy, the second row, first column. What is that? Hopefully you're getting the idea. If this is the guy I want, I need the row of the first matrix and the column of the second matrix. And again, if I want this lower left slot, we're like finding the intersection of these rows and columns. And so then it's the same deal. Like this is the spot. This guy right here. This guy right here. This guy right here. This is surprisingly hard to draw. And so same deal. First element of this row, 5, times the first element of the column, 3. So we have 5 times 3 plus 2 times 2. So it's the second element of that column. Okay, so that's the algorithm. The algorithm is to take the sum of multiplying the rows of the first array by the columns of the second array. And if you were to continue to write this out, what would you get? This row would be, we're just gonna do it just to drive it home. We have 1, and I'll make this clear. This row, this column, and that's going to give us 1 times -1 is -1. I'm going to do it in my head. And then 6 times 4 is 24. So -1 plus 24, we're going to get 23. And one more time. I want to the bottom right, so I need the row for that bottom right guy. And I need the column of where that bottom right lives. So I have 5 times -1 is -5, plus 2 times 4, which is 8. So we get 3. -5 plus 8 is 3. Okay, so we followed all these steps. We have this matrix A, we have this matrix B. I want to know how, if I multiply them, what do I get by following the multiplication algorithm? And we did all that to get our new matrix. We're going through step by step here, but we have 3 plus 12 is 15. And then 15 plus 4 is 19. And then we have 23. And we have 3. And that is our new matrix. Okay? You learned matrix multiplication. And it's simple once you understand it, but this is this is a useful algorithm. And again, addition is actually, well, I should say multiplication is just many additions, right? If I am taking, just to simple math, 5 times 6, that is 5 plus 5 plus 5 plus 5, 6 times. That's what multiplication is. Multiplication is multiple additions. That's the whole concept. And that's what we did here. So it's not efficient for computers to even do addition. It's like you're usually doing matrix multiplications so that you just bundle all those additions all together, and it's faster. Computers are all about the less steps you have to take to complete an algorithm, to process some data, the better, because computing time, it takes time and it takes energy and it's expensive. So our job as a computer scientist is to create an optimal algorithm. You can't really optimize this. This is just core foundational algorithm, matrix multiplication. But in a way, it's an optimal version of addition, if you think about it. All right, so, and my math was right. We got 15, 19, 23, 3. And when I was not being recorded or under pressure, the same deal. So we did our math right. And that's what this notation does. It just tells you how to find the matrix multiplication. And then again, we have some scary looking math. At least I think it is intimidating when you first look at it and make this really big. We have, there's our indices again. So we have each element of our new matrix C is equal to this stuff. What is this stuff? This is the summation notation, which just means you're adding things up. And then we have A, where we pick a row. This is going to twist your brain if you haven't seen it before. But if you remember, when we were doing this, I picked a full row for the first matrix. And then I had to go and step through each element of that row, right? And then for B, I picked a column. And then I had to step through each element of that column. Okay, so the first one, I fix the row. The row doesn't change, and then I step through the row. And with B, I fix the column, and then I step through the column. That is what this means. So I want, let's say this is 1, 1, C sub 1, 1, which is, or even just with our current example, I want C sub 2, 1, which is this guy. If you have OCD, I apologize. That's not going to get any better with all my squiggles. But if I want C sub 2, 1, that's the element that I want to compute for my matrix multiplication. C sub 2, 1. That's equal to A sub 2, lock at the second row, like we did. And then K changes. This is a for loop. If you worked with for loops before, you could say for I is equal to 1 to 10. And then you're going to iterate. You're going to say I is equal to 1 and do some stuff. I is equal to 2 and do some stuff. I is equal to 3, do stuff. 4, stuff. And you just, that's a for loop. You repeat. That's what that summation means. And if you don't fully understand the math behind this stuff, it's okay. It takes a lot of practice and a lot of time to understand the mathematical notation. But the whole purpose of writing this out is, instead of having to, like, I've been talking a ton about just matrix multiplication. I've just been blabbering away. If I tried to write down everything I just said about matrix multiplication, it takes up a lot of space. Like it takes a lot of words to describe matrix multiplication. But if you understand the mathematical notation and how to follow the indices, I can say everything that I have said about matrix multiplication in this expression. That's it. That's the beauty and the benefit of mathematics, is I can use symbols that have logic associated with them. And instead of having to use the English language, or like a human language, English language, to say all this stuff about my algorithm, I just write this. And I say that's matrix multiplication. So yeah, that was the formula I'm pointing to. All right. Lots of blabbering, but I think it helps things cook in your mind. So if we want to do matrix multiplication in Python, we again define our arrays, our 2D arrays to define our matrices. And then we call np dot is our function. Like I was saying, it's the dot product. And we just pass it to matrices, A and B. And I run that, and there we go. We get the same result. So one rule of matrix multiplication is that these dimensions have to fit with each other. And they fit on like so. So we have, this is m by n, like I was saying the notation was. And this is also m by m. So in order to do this multiplication, the inner numbers have to align. So right now we have A is a 2 by 2. And if I want like the dot product of matrix multiplication, this is just the shape of A. And then the shape of B is also 2 by 2. This is okay. This is allowed because these are the same. This is just a rule of matrix multiplication. So if I had a different matrix that was like 3 by 4 in its shape, so it was 3 rows and 4 columns, and I wanted to take the dot product of another 3 by 4, this is not allowed because they're not equal, these inner dimensions. So if you tried to do your matrix multiplication and you just walked through and did this step-by-step of different dimensions of matrices, you would see that you can't follow through the algorithm's steps if these inner dimensions aren't the same. Okay? If this is feeling like a drag, it kind of is. There's nothing super exciting about matrix addition and multiplication, but every step of this notebook levels up. And it requires you to know the addition, the multiplication, each of these things to get to the end. Okay. So here we have what's called the determinant. And the determinant, I'm going to erase all this. The determinant is a more advanced topic. So I'm just going to stick with like the general ideas. We can start out with a drawing. So let's say I have, this is where I'm going to start introducing the graphical side of linear algebra. Linear algebra is composed of space, like making operations on space. So as a real world example, we keep going back to like the images. If I want to rotate an image and my image is just a bunch of pixels that is a 2D array, and I just want to rotate it 90 degrees, I can do that with matrix multiplication. I can have a special matrix that is a rotational matrix, and if I multiply it by my picture image, the result is going to be the image rotated. You can create a matrix to flip the image. You can make a matrix to turn the image upside down. There's really no limit. You can this is where linear algebra is like very heavily used in editing software, but also to zoom out for a second, a neural network. A neural network is a lot of matrix math. It's just fancy matrix mathematics. Neural networks are used for things like identifying objects in video. So Tesla has self-driving cars, at least they're trying to work towards, and they have to identify objects on the road. And one way to try to do that is you have a video stream, and that video stream it's a stream of images. There's like a frames per second in a video, right? So if you have 60 frames per second, that's 60 photos that hit your brain in 1 second, because video is just photos. It's just many, many photos is all that video is. And so if you want to pick out targets in a video, then you can use linear algebra to pick out certain patterns of a car in those pixels. It's just recognizing patterns. So that's kind of the real world direction of where linear algebra goes towards in matrix multiplication and how it's useful. So going back to here, this is we're working up towards that type of application of a more robust technique called eigenvalues and eigenvectors. And so we'll get there. This first piece that we're now trying to learn, we've just talked about addition, we've just talked about multiplication. Now we're going to talk about the determinant. And let's say I've just got this shape. And actually, I won't even do that. I'll make it a square. Okay. And it has some area. And I want to, this could be represented as a matrix. And I do some form of matrix multiplication that stretches out this shape so that like I have some matrix A, the original A, and then I have another matrix B. That's the transformation one. and I want this new matrix multiplication. So that could stretch A to be something like this. So that's called a linear transformation. Is you have a matrix, and what's even a step back is these shapes can be made up with vectors. So a vector, all that is just a arrow. It can be represented as an arrow in space. So this could be, you'd write this as V1, and you give it this little squiggle as a vector. And then I can have, this is all in 2D space, I could have another vector that's in this direction. And I say it's V2. And this vector, V1, could have like, let's say this is -1, 1. Going back to XY coordinates. As you can see, I'm going back on like original algebra, pre-calculus, just simple plotting. Again, post a comment or a question if this isn't making sense. But this is how I would write this vector. And I actually could write this black one, V1, is equal to -1, 1. So this is also a matrix, but it's just a single column. So that's a common rate. That's what a vector is, basically, is a single column with however many rows you need to describe your vector. And this one here could be V2 is equal to, on the x plane, it's -1 still, but now on the y, it's also -1. And so I could write that a matrix is equal, and actually, this is a different one. You can say A is equal to those two matrices. And this just now, all that's doing is saying, okay, I've got a collection of vectors. And that's it. It's just a way to organize them and group them together. So going back to our example of, or this new topic to learn, the determinant. The determinant is just a way to measure how much a transformation, so like matrix multiplication, how much it stretches space. So maybe I did a different transformation that like to this space of the purple space that made it squish it, like, or shrunk it. It was something like this, and now it's all small. That would be a small determinant. Whereas if this shape got stretched out and bigger to this orange one, that would then be a large determinant. So if I have a large determinant, it's like stretching space out. If I have a small determinant, it's shrinking. So I'm not going to get into, there are steps to find the determinant. It once again is like I have drawn out, okay, we've got a 3x3 matrix, and I've got each element labeled as a different letter. if I want to find the determinant of A, this is how I do it. It's just it's a special set of steps where you plug in your values of your 3x3 matrix, and that will give you just a number. It's not a matrix. It's just 5 or 2. It's just one value. And the larger your determinant, the more that this matrix, if you multiply, it stretches things out. Okay? So again, don't worry. Here's some general notes on if the determinant is greater than 1, we're stretching. Because we could be working in 3D space too. So maybe I've got like a cube in 3D space, and I have this matrix multiplication that stretches out and makes the cube bigger. Well, I can quantify that as having that matrix multiplication had a determinant that was greater than 1. And then with a determinant is less than 1, maybe I shrink the cube or I make it thinner. Or if I have just a square, I make the square thin. You're shrinking space. And then say if the determinant is equal to 1, that could be the same as like where we had that picture example and I want to rotate the image. That operation would have a determinant of 1 because I didn't change this photo other than rotating it. I didn't enlarge the photo. I didn't stretch it out. All I did was just rotate it and change its orientation. Okay.
Can I ask a question?
Yeah.
If matrix A is say like 5 by 5, finding the determinant for that, is it a different equation than what you have listed here?
It is. It's
okay.
So if I had like the determinant steps are actually pretty gross. They're different for each shape of matrix.
Okay.
If I had just like a 2x2, this 2x2 would just be A times E, and then minus D times B. That's just the steps to find it for a 2x2. And so
you have to kind of have to memorize the determinant steps then for each.
Yeah. Yeah, okay. This is not something, and actually you don't even really do, like, you can memorize. It's important that you understand, like, oh, okay, it's just these operations. But as soon as you get the idea that I'm getting a single value out of a matrix, that's what matters. And then what the value of the determinant is.
Because the computer will do it for you.
Actually, that's most of linear algebra. But as you go higher up the knowledge tree of linear algebra, everything builds. You have to understand your foundation to understand what the heck is this library doing. Because you're not going to be able to use the tool if you don't at least understand the concepts. So if just as like an analogy, if I'm building a home and I have a screwdriver, I don't need to know like the physics of the motor in the screwdriver, but I need to know like, okay, here's a button on which direction, on what speed, and it's meant for screws, or to drill a hole. The bigger concepts you need to understand. You don't necessarily need to know every single detail. Because so we have this matrix. And if I want to compute the determinant using NumPy, I can say I have some auto suggest. I should be able to turn this off. We'll see, because the auto suggest is a little annoying on these notebooks. It tries to use AI and complete everything for you. Here we go. Might just need to bear with that for a second. But it's already telling you I'm using NP, that original package that we talked about, NumPy, dot, and then I have this sub package, linear algebra. and then another dot, determinant of A. And you don't have to memorize like, oh, I have the numpy package. With enough use, you'll come to memorize I have the linear algebra sub package and the determinant. Like, this isn't very complicated. It's just this function call, and then you pass it a single matrix. But you can use tools like, you can just Google, how do I compute the determinant of a matrix? And you can get that, or just use, ChatGPT. Those types of, like, finding the exact syntax doesn't need to be your main concern. Your main concern should be, all right, I understand what a determinant is. And it's that concept of stretching or shrinking space. And it gives me a number to work with instead of a matrix. I get a number from like a 3x3 matrix. So anyways, if I print this determinant, I see that the determinant is 0 for this particular matrix. And that's nothing, that actually is meaning it's collapsing the space. So like if I had a shape, if I had a 3x3 matrix, such as this one, then if I, actually I need to, I don't want to speak, that's a note I have to add because I don't recall this being 0 from when I last ran it. So maybe I accidentally changed something. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's supposed to be 0. So that was a special condition on it being 0. So I'll add a follow up to that, to the post, like where you see in Codecademy. Because I believe it collapses space when you use this to multiply something, but I want to make sure that's the correct interpretation. So I'll get back to you guys on that. Let's see. Hopefully, does anyone have any current questions off of what I've said so far? We've got 30 minutes left. So I also want to give an idea of eigenvalues and eigenvectors before we get into more code. Okay. Things are going to get a little more interesting, hopefully. So I'll grab all this. All right, so let's say we have 2D space again. And I have a couple of vectors. I have this vector, v1. I've got another vector this way. And I have one more vector over here, little guy. All right, and so you could write a matrix and have it equal these vectors. Like, again, if I could just write this vector out as like a single column, but I can combine all of them into one matrix for notation's sake and to combine things. But that's what this matrix can represent. And so let's say, I multiply some other matrix by these vectors. So I had like another matrix B. And when I multiply it to A, that's the linear transformation we were talking about, where maybe we rotate it or we stretch it, or like something's going to happen to all these vectors when I multiply them by matrix B. And for example, let's say that these are just the new vectors after doing that. Let's say that V2 went to here. And then let's say that V1 just stretched. And then for this last one, that it turned into this. Okay, so all the vectors got changed from this matrix multiplication. We had some new matrix B, we multiplied, and they all changed, except one of them is special. And so I saw that there was a few people who were here for the first session. Is anyone willing to take a bet on which of these vectors is an eigenvector and why it's an eigenvector? It's a funny name, but it has meaning. So I hope I say your name right, Lauber. That's correct. Is V1 the vector that just gets stretched? That's actually a very important quality of a matrix. So I have all these vectors. I did some matrix multiplication. They all changed. But then one of them actually didn't change. It just stretched in the same direction. And when you have a vector like that in a matrix, that's called an eigenvector. And maybe for a different matrix B, if I multiplied, then that red V1 might actually shrink, or it might, like, it could even go in the opposite direction. It could go like that after the transformation of this space. But the important thing is it stays on this straight line. And no matter what different transformations you do to this matrix, so I got some glare. Get that real quick. No matter what you do to this, still there. I get a weird angle at this time of the year with the sun, and it kind of becomes a pain. But anyways, if it's only stretching or shrinking along this center line, then it's an eigenvector of a matrix.
Eigenvector of matrix.
Sorry?
Eigen.
If you can, just double check that you're on mute. I'm happy if you want to ask a question or have a comment or anything. But just double check you're on mute for everybody. Okay, so why are these important? I will say I'm condensing like 5 months of information into just these core topics because, again, I want it to expose you all to like what is linear algebra, why is it important? Okay, and so you just hopefully got an idea of an eigenvector. We have these vectors, some of them change when you do different matrix multiplications, but then you might have one or more who only stretch or shrink. This is important because these types of vectors can be directly used in really great data techniques. So one of one technique that I think is really interesting and applicable is, oops, I think I can do a line. Maybe not. Okay, well, bear with me. If I have time series data, and time series data, if you haven't seen it before, it's just a lot of data points over time. So you will always have the x-axis to be time, t, and then maybe I'm plotting global temperatures, and I have that as like Celsius or something. Okay, that's my x and y. And then I have data points, and we could have like, this is 1800, 1900, or maybe that's too much, but like decades or something. And I've got data that looks like this. Oops. Give me a second, and I'm going to create a pattern. And you might start seeing the pattern. Okay, so I just made all these squiggles and points, but this is how real data could look. And actually, it does look like this. And so I'm plotting global temperatures, Celsius. And this is time series data because it's all plotted over time, and we've got lots of it. So we were just talking about eigenvectors, and I can represent this data as a matrix, and I could have, if it's only time and the temperature, then we might just do like, that's just a single row of data, like over time, or a 2D row, where our rows could be time, our columns could be the temperature, and that's how we represent this data. We could have more variables. We could have, the amount of CO2 in the atmosphere. I'm not trying to get political or anything, but just like how we model climate. What are factors that may contribute to temperature? And if I added on more variables to this time series data, instead of 2D, it could be 3-dimensional, or it could be 4 or 5. And that just means I'm adding more like, how much forest is there on planet Earth at any given point in time? That's another variable that I can add to this data. So right now we're just looking at 2D data. It's just time to temperature. But as I get multi-dimensional matrices, all that means, like if I'm in the 5th dimension, that's not like a weird physics concept. That just means I have 5 different factors, variables that contribute to my data. And so, Glauber, the question on the data set's regression can be or is the vector itself. This is where eigenvectors come into play. So you can use eigenvectors in a special way to where you extract what's called principal components. And I know I'm just saying like a bunch of jargon, but these are names. What principal components are: they are built from eigenvectors of your data. For example, like you have your matrix of data and you find the eigenvectors, you can use those eigenvectors to build the principal components. And what those are, let's say this first principal component, P1, is this. So if you've seen regression before, that looks like a regression line. but there's more to it actually, because if you're just doing standard regression, linear regression would just fit your data with a straight line. And it does that by just trying to minimize the distance between this new line you create and all the data points. So with like regression, it's not this curved one, it's just straight. And again, it's just trying to minimize the distance between the dots and this line that you constructed, okay? Whereas a principal component, it captures the structure of your data using eigenvalues. So there are parts of your data that don't change, that like have a pattern that's baked in. This is that first, like most important pattern, is that it's this slow upward trend. The second principal component, again, these are built with eigenvectors, is that it's this, it could be this. And you might think, what the heck is that? It could be a sine, like if you are familiar with sine or cosine waves, that's just, you know, it's just a cyclical pattern. And this could be the Earth with winter and summer, or its rotation around the sun. It's like slightly elliptical, but there's peaks and dips. You know, maybe we're just looking at North America, and then this would be even stronger of like it's cold in the winter and then it's warm in the summer. So this is our second principal component built from our eigenvalues. We have this data, and then one of the patterns in the data that's baked into it is this cyclical pattern. And if I combine these two principal components, and I say, let's just say, we'll say X. It's this new data estimate, and it's equal to P1 plus P2. Why does it do this? There we go. Well, now I'm actually going to fit my data pretty well. It's going to look something like this. And what you might see is that we had this first principal component, which is like the core. It describes the most amount of our data. There's a word called variance in statistics. And variance describes just how much, you know, variation there is in your data. Is your data like really consistent and tight together? That would have a low amount of variance. Is your data super spread out and it's hard to guess what the next data point is going to be? That would be high variance. And so just using the first principal component and the second principal component built with eigenvectors from your data, we can extract the core pattern of your data. You could use this for earthquake data, which is like super, super noisy. I'm trying to track like the seismic activity of the earth. But if you apply this technique and try to extract the principal components from the eigenvectors from seismic activity data, you might pick out a pattern like, oh, every 7 years, this location on the West Coast starts to have more earthquakes. And that's a very valuable thing to know. So you can use This is called principal component analysis. I'm going to type that in the chat. You'll probably see things that are complicated and a lot to take in, but that's why I'm trying to give an introduction, because it's all about taking things a piece at a time. You all now understand matrix addition at least better than you did when you walked in here. You understand matrix multiplication better. You understand the determinant, which is like how much things stretch or shrink. You use the determinant to find eigenvectors. There's all these steps that I haven't stepped through yet, but it's algorithms. And, it's tough to fit all of this in even with an hour and a half. Like I said, this is a months of material that I'm throwing your way. So what's important, I think, is to see like, oh, this is where this leads to. Like I can actually get really insightful data analysis. You can continue on to be like, say we're at the present year 2024, and I want to make predictions. I want to say, okay, following this pattern, like what's it gonna be in another 10 years? And I can make a forecast off of that. And I can say we're estimated in 10 years to be at this temperature because this is the pattern we've observed for 300 years. So it doesn't have to be climate. It can be another example of using these techniques is movie recommendation systems. Think of Netflix, where Netflix has so many movies and shows and like just so many possible titles for people to watch, millions of them. And then they have millions of customers. So how in the world do you map the like the best, this is my closing statement. How do you wrap up the best recommendations for given users? And you can do that with eigenvectors and principal component analysis. You can compress all that data to the most important component. So you might not be able to say, hey, this user will want exactly this title, but they do. But maybe they're a lot more into fiction or comedy or whatever. So I know I got much more conceptual towards the end, and I didn't go as much into all these future steps. I try to make the instructions as clear as possible, so I hope you take a look at this notebook and try things out for yourself. And if you have a question, like I have comments all throughout here of like solve for different things. You can try and work through this notebook. And if you have questions on how to do it, drop a comment on the event and I'll answer them. So I know that was just a lot of information. Thank y'all for joining. I hope that this was useful. It was difficult to like cater to the people who have been here before and the people who haven't seen any of this stuff. So I kind of tried to just make it farther than the last time around. But that's all I got. So Stephanie, take it away.